Thank you. So I'm Colin Sullivan. I'm product manager at NATS. And today, Derek Collison, creator of NATS, Waldemar Quevedo, and Jaime Piña are going to be presenting. We're going to cover an overview of the NATS project, new features, and our roadmap, and then we've got some demonstrations for you. So an overview of NATS. What is NATS? NATS is a 10-year-old production-proven cloud-native messaging system. We built it to be cloud-native from the ground up. Ease of use is really, really important to us. So to that end, we built it for developers and operators that just want to do their jobs, that don't want to have to learn about messaging, don't want to have to deal with the details. And we want to spend more time doing their work, less time worrying about distributed messaging infrastructure. Our DNA includes performance, simplicity, security, and availability. That's what's built into NATS. We've got multiple qualities of service, at least once delivery, at most once delivery, support for multiple communication platforms, and over 33 client language bindings. We joined CNCF in 2018 as an incubation project, and hope to be graduating soon. We've got a great ecosystem. We've got over 1,000 contributors. 100 of our contributors have more than 10 commits, so these are people that consistently contribute. 75 public repositories across our repositories. We have 15,000 GitHub stars. Between our two servers, we've got about 100 million Docker Hub pulls. We've a healthy community in Slack with over 1,600 members, and a good cadence of NATS server releases with about 5 a year. NATS was created in Derek Collison. Derek has been solving the really hard problems in distributed computing for over the last 25 years. Derek's history has been at TIBCO. He was a technical director at Google. He architected Cloud Foundry, where NATS was invented. He was CTO and chief architect at VMware, founder and former CEO at Observable, and now he's CEO at Synadia, where a lot of the NATS maintainers work. Derek's built a highly experienced messaging team around NATS, and to complement that, we do have a very engaged user community. Our end users, if you look at the slide, our end users don't seem to fit in one particular vertical. That's because NATS is a horizontally enabling technology. You can use it to solve many different problems in many different business cases. We've got a number of NATS clients that are maintainer supported, fairly popular. We get a lot of contributions to our clients. And NATS use cases include cloud messaging, which are microservices, event and data streaming. This is observability and analytics. I want to request information from services. I want to save data off and replay it later. Or command and control planes. We also work well in IoT and edge for telemetry, sensor data, command and control again, and we're finding more and more people are using NATS to augment or replace older messaging products that don't work as well in the cloud. Let's talk a bit about message patterns. We try to put message patterns in our discussions in two buckets, streams and services. A stream is a flow of data. It may be persisted, it might not be, but streams can fan out or fan in. And then we have services. A service is something that just does some work. You ask it to do some work, and it returns a result back. And we can load balance services. NATS can act as a layer 7 load balancer. Underneath these two buckets, there's 3 patterns that you use in your applications: request reply, publish subscribe, and load balance queue subscribers. But before we get into these patterns, let's talk about subjects for a second. A subject is simply a string that represents interest. In NATS, you don't address your endpoints. Everything connects to NATS and receives data based on interest represented by a subject. So a simple subject is just a string foo. You can tokenize subjects, and when you tokenize subjects, you can then use wildcards to create some fairly complex subscription matching. NATS is interesting in that everything, including request reply, your RPC style, is pub sub. So if you want to look at what's going on in the entire system and you have permissions, you can actually subscribe to everything and watch everything that's happening in the system, which is really good for debugging. And then we have unique subjects that you can generate that are unique, and that creates that one-to-one relationship that you might have with a microservice. Here's a more practical example of what wildcard subscribers look like. So given these subjects with sensor data, USCA San Diego, sensor errors, USCA San Diego, and then maybe some in London, this demonstrates how you can subscribe to get all US data by subscribing to sensors.data.us.anything afterwards. You can subscribe very specifically to get data, in this case, only data from London. You can get errors worldwide and all errors and data in the UK just by manipulating some of your wildcard subscriptions. And this offloads a lot of this work that might happen in your application, pushes it onto NATS, which does it very, very well, and also minimizes your network traffic. So with the request response pattern, this is a one-to-one pattern, and using unique reply subjects, clients make requests to services, creating this one-to-one relationship. Publish subscribe can be a fan out. So you can publish to foo, and every single subscriber that's subscribed to foo will get the data. This is a fan out. You can also fan in. You can have a lot of publishers on foo and one subscriber on foo that then aggregates this data. We have load balance queues. When you have subscribers subscribe to the same subject, you can optionally give it a queue name, and that groups them together. And then what the NAT server does is it load balances messages that are going to these queue subscribers. So the first message will go to one, the second one might go to another, third to another, and so forth. These queue subscribers are randomized, which over a period of time works out to have an even distribution. We have, again, the wildcard subscribers showing how tokenized subjects or tokenized subscriptions can match various subjects. Now let's talk about performance, scalability, and resilience. Performance, NATS can perform, I think it's over 18 million messages a second now, but on some decent hardware, 18 million messages a second with one server, one data stream, and up to 80 million messages a second per server with multiple streams. You might be saying, well, I don't necessarily need that. But what this translates into is scalability. If one server can do 18 million messages a second, as you grow your business, as you expand, you aren't going to have to change your server topology until you really, really, really grow. It's going to last a while. How do we get here? We get here through decisions in what we do in our design and R&D. So we design for scale. That means, let's say we're adding a new protocol message. Instead of having the burb be 5 bytes, we have it 2. Doesn't seem like a big difference, but when you scale to millions of messages a second, it can have an effect. We do a very, very careful analysis of the fast path. So as messages are flowing through the servers and the clients, we're very, very careful about how we lock, very careful about moving memory around, about these operations that in normal conditions don't really make that much of a difference, but at scale, at performance, they can actually add up to make quite a big difference. We're talking millions of messages a second by avoiding a few memory moves. Just as important as what we look at to get this performance is what we look at not to implement in the fast path. So exactly once message delivery, transactions. We don't have message schemas built in. We don't have message headers built in. That's not to say we won't do this someday, but they aren't going to be part of the fast path of the NAT server. They're probably going to be some sort of subsystem. Health and availability of the system as a whole is prioritized. So traditional messaging and some of the legacy messaging products they take effort to prop up and try to deliver that message to a poorly behaving consumer. And when they do this hurts the system as a whole. You're taking resources away from the system as a whole. So NATS has taken a different approach. We have selfish optimization in the servers. So if a poorly behaving client, if a client's not keeping up, the NAT server chops it off. At that point, someone in DevOps might take a look, determine that that node might need more resources, figure out maybe there's something wrong with the code, but that keeps the rest of the system as a whole performing well. We have full mesh clustering of the NAT servers to make sure NATS is always available, and server and client connections can self-heal. This creates a dial tone, a utility that you can use in your enterprise that's always on and always available for your communication needs. Simplicity is really important to us. So the servers are a single binary. The NAT server is about a 7.8 Docker image. We have a text-based protocol that, let me clarify, there's sometimes some confusion here. While the protocol verbs in itself are text-based, our payloads are agnostic. We can do binary payloads. But what's kind of cool about the text-based protocol is it makes it really easy to create clients. We're very low configuration. Clients only need a URL and credentials. Servers auto-discover, so you don't need a lot of configuration in the servers. And then you can share configuration files amongst servers. You can include configuration files in other configuration files, making it easier to configure. And there's a very simple and straightforward API. We have auto-discovery built into NATS. What does this mean? This means as you cluster NAT servers and you add a server into the cluster, the servers talk to each other and adopt this new server into the cluster, adding it in as full mesh. There's no additional configuration you need to do other than when you're letting this new server join the cluster, you point it to any other NAT server in the cluster. This means in the cloud, you can scale up or scale down your cluster as you need to. But there's more in that this topology is also pushed onto the clients. So that means a client can fail over to a server it never originally knew about. These are great for rolling upgrades. As you're rolling upgrades, you take down servers, put new servers up, and the clients can always fail over and have another server to back up to. We support 2 delivery modes, at most once, which is core NATS. This is no guarantee of delivery. Messages can be lost. Applications must detect and handle these lost messages. It sounds fragile, but if you think about it, that's how the internet works today. And it works pretty well, right? Request, reply. I send a request, I wait for a reply. If I don't get one, then I just send it again. That's actually pretty simple application logic. And we've seen it work extremely well in scalable and highly scaled systems. But then we also have at least once, which is NAT streaming and JetStream. This is where a message will always be delivered. In certain cases where you have errors, a message might be delivered twice. Some systems offer exactly once. Offline, I'll be happy to argue that it's unnecessary because it's very complex, and inevitably, this complexity makes it very, very slow. Happy to talk about that offline. We could spend hours talking about exactly once. With NAT streaming and JetStream, NAT supports at least once delivery. You can replay by time or sequence number. It can act as a last value cache. You have durable subscribers, which are subscriptions that receive messages, and then if something happens, you lose your connection for a while, it comes back up, it'll just pick up where it left off. You have rate matching. You have memory file or database storage. High availability, we've got a couple different fault-tolerant modes, and then you can scale through partitioning. That's vertical partitioning, not horizontal across servers, so no such thing as rebalancing in NATS. NATS gives you a number of building blocks to build very complex or very simple topologies, whatever you need. At the base is a standalone NAT server. The standalone NAT server can be clustered to form a cluster with a number of other NAT servers. These clusters can be connected together to create what we call a supercluster. These are great for wide geos. I'll go into more details on that in a second. And then we also have the concept of a leaf node, which is a NAT server off on its own, connected into a supercluster or cluster. NAT server clusters are full mesh, one hop. That's great for preventing for loops. Messages only traverse clusters where there's interest. So if the client on the one client is sending messages to another client, there's no interest in another server, messages will only flow where they need to. We've got superclusters. Again, clusters of clusters. Superclusters aren't full mesh like basic NATS clusters. It's a spline-based technology where each server is connected to at least one other server in the other cluster. And these connections are optimized for WAN links. So they're low chatter, but yet you still have resiliency. If you lose if you lose any but one of these connections, you'll still have connectivity. Multiple clusters can be linked together to form superclusters, so you can build just really vast deployments over WANs. And locally, you'll get the performance and super high resilience and scalability within a local cluster, yet have connectivity all over the world if you want. And then we have leaf nodes. A leaf node is a single NAT server connected to a cluster or remote server. They extend clusters via hub and spoke technology. Leaf nodes allow you to bridge separate security domains. In a bit, we'll talk about NAT security. But let's say you've got a different type of security you need on the edge. It can be physical. So for example, your clients can only connect to a loopback address. That is a leaf node that is then connected to a NAT supercluster. These are ideal for edge computing, IoT hubs, data centers, what have you. There's many use cases for this. And then they transparently bridge on-premise and cloud deployments. One of the cool things about NATs is your clients don't care anything about the server topology. All they need is a server to connect to. So you can change your back-end topology without touching your clients at all. Here's a hypothetical global deployment. There we go. Here's a hypothetical global deployment with a cluster running in Kubernetes in San Diego. Let's say you have a cluster in Berlin running on virtual machines, cluster in London. You've got a leaf node off of Berlin. This could be running on a small device. We've run NAT servers on Raspberry Pis. You can have a leaf node and remote cluster elsewhere, which might be a backup data center. So you can build, back to this. So you can build very complex topologies with these building blocks. Now, one of the benefits that we've added in these global topologies is geo-aware queue subscribers. So we're going to take a very, very simple queue subscriber example. Both of these subscribers are subscribed to foo. They're part of the same group, but they're spread across two different clusters. Message flow will only go to the one because the local queue subscriber is always preferred. If you need to scale, then locally, you just add more queue subscribers. But what happens when you lose this? Your local queue subscribers, you've lost all your queue subscribers locally. Then, and only then, will you go to the remote cluster. If there's multiple regions, the lowest RTT is chosen. So we attempt to give you the best latency. And when you bring your local one back, message flow returns to prefer the local queue subscriber. So what does this mean? You have disaster recovery. With runtime scalability, you can change, add, scale up or down at runtime with no configuration, and you'll get the best latency. Security is very important to us, and we support all, what's becoming the basics. We've got full TLS support, we support CAs, bidirectional TLS, we default to the most secure ciphers, but if you need to, you can add other ciphers. We support using the DN or SAN-in certificates as an identity in NATs to map that for permissions, for pub/sub permissions. We support standard user password auth. As I mentioned, we have permissions. You can decide what identities can subscribe to or publish to what topics, what subjects. And you can change these at configuration reload at runtime. And you just send the NAT server a signal. It'll reload all these permissions so you don't have to have any downtime for this. And we have an operator mode. Back last year in NATS 2.0, we created another security scheme that's actually very, very powerful. In this, you have a thing called an operator. An operator is your enterprise. It's sort of your global deployment. You have, under your operator, you have accounts, and under accounts, you have users. So an operator serves as a root of trust for the system. This is, again, your enterprise. Your operators create accounts for account administrators. An account just represents an organization with a secure context. It could be a group of microservices. It could be an organization in your enterprise. It can be really whatever you want it to be, but it provides a secure messaging context. And I'll talk about this in a minute. And accounts can define their own limits. And then they can also securely expose services and streams for cross-account communication. And then under accounts, you have users. Here's where you can assign very, very specific credentials and permissions for user access into the accounts. So an account is an isolated communication context. And what it has done for NATS is it's created true multi-tenancy within NATS. You have your NATS deployment. You have accounts configured on that. An application can connect anywhere in NATS, and where that account lives, that application can connect, and it acts, if you will, as a container for messaging. This separates your deployment from your business use case. So now, if you want a data silo, you can define it, and it doesn't have anything to do with the topology. You aren't forced into creating data silos because of technology limitations of your distributed computing system. They're easy, secure, and cost-effective. So you've got one NATS deployment for your operators to manage, and then it's decentralized. If you let organizations have their own account, they can create users all day and create and revoke users, and your operations doesn't have to worry about that. Your account owners do. It's a distributed, decentralized security. And then you can share data between accounts. You can create secure streams and services. So if I have an account and Derek has an account and we want to share some data, I export a subject that some of my microservices might publish on. Derek's interested in that. Derek imports that subject. Only when we both mutually agree will that data flow. And that, again, helps with decentralized management of security. This is going to be very, very important as IoT explodes. It's already exploding. As IoT continues to grow, how are you going to manage these billions upon billions of devices? Well, you have to do it in some sort of distributed fashion. To do it centrally would be quite a headache. Behind all this are N keys. N keys are ED25519 keys that NATS uses to sign and verify accounts and users and the operator. They're very fast, resistant to side channel attacks, and the way we use them is in a way that the NATS servers never, ever, ever need to see a private key. The server sends a nonce during a connect, and then the client signs the nonce with its private key, sends it back to the server, and then the server verifies it through the account key. This allows us to begin to create a zero trust system. As we're moving forward, we're going to add some new features that our end goal is a complete zero trust system. And then we have JWTs. JWTs encapsulate and hold all the information about users, accounts, and permission sets, and associated permission sets. So in operator mode, JWTs are used to represent a user, an account, a cluster, or server. They contain an account end key, the public end key. Again, private end keys are kept by your clients. They're never read, accessed, or accessed by the server. We have a public end key, which is just your subject, a friendly name, permissions, limits, and a not before and not after. So I create a user, and I say this user won't be valid until tomorrow. And then, by the way, this user is going to expire next week. We've got a tool to create JWTs. You can create the operator accounts and users. You can create imports and exports. You don't have to mess around with JWTs. We've got a nice client tool to do this. And then this tool can also deploy JWTs. They can upload to something called an account server or create configuration files with these embedded JWTs for you. So you're going to have all these users and accounts floating around. You need a way to manage them. In the NATS server, you specify a resolver. And we've got two flavors of the resolver right now. What's called a memory resolver, which basically just means look in my own memory space from what I've configured in my configuration file. These are JWTs embedded in the configuration file. They're ideal for static deployments that aren't going to change a lot. You don't have a lot of accounts. If let's say you're creating a SaaS system using this, then you may have a lot of accounts being used for NATs, used in NATs. And in that case, you can use an account server. So all your servers, let's say a user tries to connect, and the server says, hey, I don't recognize this account. He goes and tries to resolve it with an account server that looks it up, feeds it back, the server caches the account data, and you can then manage millions upon millions of accounts without having them configured in every server. It supports mirroring for performance and backup. And these are used when accounts are frequently created or expired. So some of the new features in NATs. We're introducing JetStream. Some of you may have been hearing about this for a while. We built JetStream to be the next generation streaming system. And we had a number of goals. You know, it's like the rest of NATs. It's got to be easy. It's got to be secure and work well with NATS 2.0 security. It's got to scale. It's got to scale horizontally. As ingestion rates increase, we want to be able to scale out without changing anything in the clients. We want to support multiple use cases, self-heal, always be available like the rest of NATs. One of the things we've heard a lot from you guys, our ecosystem, was that the NAT streaming API was too far from the NATS core API. So the NAT streaming, or the NAT JetStream API will be built into the NATS core API. It'll use NATS core. We are also going to support wildcards. The system has to allow NATS messages to be part of any sort of a message grouping message set as desired. And we're going to remain payload agnostic. Also, no third-party dependencies. So JetStream's well on its way, supports at least once delivery, much of the same things. Those of you that are familiar with NAT streaming and what we talked about earlier, supports much of those same things. It's going to be embedded as a NAT server subsystem with an option to enable. That means in your deployment, you might have a dozen NAT servers, and maybe 4 or 5 are JetStream enabled. Wildcard support supports NATS 2.0 security, data at rest encryption. One of the things we've heard a lot from the community is, how do I erase an individual message? This is all driven by GDPR. We're going to support that now. We're going to support where you can write over a message with a random series of bytes, effectively deleting it from the system. Horizontal scalability, and then you can persist data via message sets or replay with observables. Message sets are groups of persisted messages. They're created at runtime, no need to provision them ahead of time, and they have various policies set per unique message set. Observables are how you pull data out of the system. They're how you get data out of message sets. And they've got some policies that dictate how these message sets are consumed. So message sets are defined by subjects, including wildcards. So a group of subjects represents a message set. A retention policy limits a replica account, how much risk you want to assume versus performance, and storage type. So message sets support various retention policies that they determine when the data is rolled off. So you have a stream. So a stream just means I'm going to set some other limits, and that's when data is rolled off. I've got interest. Messages are retained until all other observables, either durable or ephemeral, have consumed a message, and then it's rolled off. Or work queue, which allows multiple consumers to pull data from a message set. Limits are applied, which is similar to our streaming product today with max messages, max bytes, and max age. And then we've got the other side, the observable, where we're going to pull data from a message set. We're going to pull data from the streams that we have saved off. So you have a delivery subject, an ACK policy, durable name, start position, start type, a replay policy, or a subset. So let's say there's an existing message set out there that has several subjects. You're only interested in one. You can actually pull just a subset from that message set. An ACK weight and ACK policy. So ACK policies dictate how the observable behaves when they're reading messages. I know this is a lot of information. I'm going to try to distill it down. But indirectly, it just defines what a lost message means and defines your performance characteristics that you want. So none is just turn on the fire hose if I miss a message, so be it. All means that you're going to give me I'm going to receive a stream of messages, and let's say I receive 10. when I ACK number 10, it implicitly ACKs all messages before that. That's a very performant way of acknowledging messages I've received. And then explicit. Every single message requires an ACK or a NACK. Resend me this message. Replay policies can determine the rate of replay. You have instant, which is just replay the messages as quickly as you can. Again, turn on the fire hose. Or you have original, where you replay messages with the same timing that they originally arrived into the NAT system. This is pretty big for testing. You have those corner cases where you might get a burst of data. Some of your applications behave weird. You can replay this data to recreate that. So now that JetStream's coming out, what's going to happen in NAT streaming? NAT streaming will continue to be supported through June of 2022. We do have 50 million Docker downloads, and we know it's deployed in production globally, so we aren't going to just get rid of it. Security fixes and bug fixes will be applied. But moving forward, new NATS-enabled applications should prefer JetStream. We'll provide a migration path to use JetStream. We aren't entirely sure what that's going to look like right now, but we would love input on that. And then also new development in terms of persistence and durability is going to happen in JetStream moving forward. We've also created some reference clients for distributed tracing in Java and Go. And in this case, we use open tracing with Jaeger. Check out the repos if you want to do tracing in your application and see where messages are going, how long responses are taking. We've got that option. We've got a number of integrations with Spring. We've got a Kafka bridge, MQ series bridge. We're willing to build more bridges. Just let us know what you need. And we have service observability. So you've got the tracing and open tracing where you enable that in your application. What we've built into NATS is observability in your services as messages flow through. So you don't need to do anything to your applications. You just turn on this switch when you create a service, when you export a service, you turn on this switch, you subscribe, and you get this latency data. Again, your applications don't have to do anything for this. You get this for free. One of the things that's been happening is some of the NATS maintainers through Synadia have been going on a lot of POCs, and we're doing a lot of global deployments. We've gotten pretty good at it. We can usually do one within a day, but one of the things that's really difficult is monitoring. You need to set up sidecars, expose ports everywhere in multiple data centers, open up holes in firewalls to get all this data. So we thought about it and decided to build NAT Surveyor. So NAT Surveyor, from one place, plugs into your NATS network, and with the right credentials, you can monitor your entire deployment from a single container or process. It provides a comprehensive view. You're viewing the whole world. All you do is run it and connect. There's no sidecars to deploy. You can deploy it with Kubernetes, Docker Compose, bare metal. I personally run it with Docker Compose on my laptop, and I just plug in using kind of restricted system credentials that can only read, and I just connect to a NAT server deployment and see what's happening. It does require NATS 2.0 security and some level of system credentials. Here's what it looks like. We use Grafana and Prometheus. It's just a very easy way to monitor. We're doing, we're kind of retooling some of our Kubernetes deployments. We're gonna have a single command line to install multiple server cluster, to install NAT streaming, to install Surveyor. So it's one-stop shopping for Kubernetes. You just run this one line and you'll have everything installed. These will be with stateful sets. The NATS operator is also changing to use stateful sets internally, and then monitoring as well. We've retooled our doc. So our doc is now searchable. It looks nice. We've added a lot of content. We realize doc is really, really important for open source projects. It tends to be an area that's neglected in open source. So the team's worked really hard on documentation. What are we going to be doing moving forward? So JetStream's going to be released. Surveyor is almost ready for an official release. We're going to have service abstraction APIs. So when people are writing services, they tend to do the same thing. There's a number of things that are almost boilerplate boilerplate when you write a service. So we're going to provide an API to assist you with that. We're going to do additional tutorial solutions. What topology should I use when? How do I create these patterns that I might need? Or when would I need a certain pattern versus another? And then moving forward beyond that, we also are going to do native MQTT support. If you think about leaf nodes, you can have a global NATS deployment. You stick a leaf node that's MQTT enabled. You can connect, you can talk to many, many different devices that are already out there, already deployed, already out in the wild, and bridge them into NATS. WebSocket support. We've got edge-to-edge zero trust security that we're looking at, which would be some way for you to encrypt your messages in a way we cannot decode. And then WASM support, so WebAssembly support in the NATS ecosystem. WebAssemblies running in NATS servers that you code up, you inspect a message, might do something with it, might enrich, might send it to another subject, but everything's in your power with this message. You digitally sign it, so it's secure, and you upload it to the NATS server. And then we're going to do some some system-wide debug tooling. So now, let's start on the demos. I need a drink of water. So what I'm going to demo first, I'm going to do some demos, and then Wally's going to come up, and then Derek's going to come up and demo JetStream and talk about JetStream. So what I want to show first is I've created this. I'm going to demonstrate just the geo-aware queue subscribers. So I've got this simple replier. So this is your service. This is what it's something pretending to do some work and sending a response. I connect the NATS, I queue subscribe. I added a little bit of jitter here just to pretend I'm doing a little bit of work, and then return the response. I've got a requester. This requester I'm going to run from my laptop. This requester is a bit more involved because it's Prometheus enabled. I wanted to show you something beyond a terminal. So I've enabled it with Prometheus. I've got a little dashboard. I'm going to show what's going on with this. And then here's a Docker compose file I'm going to run locally that's going to run Prometheus, Grafana, and my requester. What I've already set up, in DigitalOcean, I've set up a responder in India, a responder in London, and a responder in San Francisco. Rather than set up an entire global deployment for the demo today, I'm using NGS, which is Synadia's global deployment. I created a free developer account last night on it and just set this up. So it makes it a lot easier. So my service, what I've done is I've taken that service requester, service replier, uploaded it up into Docker. I've got some credentials for NGS that I'm going to connect to and run. So I'm going to start the one in India. And this is just listening for messages. And here is my requester. And I'm going to run this via Docker Compose. All I do is I run the Docker Compose that I've already shown you with Prometheus, Grafana, and my requester. So now, because I'm sending this from my laptop, it's going up through the Wi-Fi, probably not getting the best latency, but going up through my Wi-Fi, up through the Wi-Fi here through the convention center, it's finding the nearest local cluster because NGS is geo-affinic, which is probably in San Fran, might be closer, and then my queue subscriber in San Fran is receiving these messages. Note that the queue subscriber in India and this queue subscriber in London isn't really doing anything right now. I'm going to reload my dashboard. And here we're already getting some latency data. You can see latencies falling into buckets of between 50 and 100 microseconds. Not too bad, not good. But what we're going to do is when we let this run. And again, remember, the data is going through my laptop, through the Wi-Fi, up to San Fran right now. So now, what's going to happen if I kill the process in San Fran? Well, right now, the requester's probably timing out, and then it's going to try to retry and resend. And there we go. London took over. That took longer than I expected. But anyhow, London took over. So now I'm sending data across the pond to London. So we're going halfway across the world and back. If I look at what my requester program's doing, we're going to see that latency spiked up to now 200. It might hover around 180 milliseconds. We'll find out. And then we'll take it one step further. So London's going. And, oh, I just lost London. All right. At this point, it's retrying, it's timing out. I think I have a 3-second timeout. And now, here we go. Bengaluru took over. So now, what's just happened? I've had 3 disaster recovery services. And the local one just died. It went to the one with the lowest latency in London, the next lowest latency. And then I killed London. And then it went all the way to India. But look, when I bring this back, there we go. I'm back online with my local Q subscriber. So this is essentially using NATS for disaster recovery for free. I think it's a really cool feature. People spend months building disaster recovery schemes. This is a really cool feature. All right. Well, thank you guys very much. And before, Wally has a demo, that Kubernetes, and then Derek's going to talk about JetStream. So don't leave yet. And in fact, we have the coolest stuff coming.
Okay. So my name's Jaime Piña. This is Waldemar Quevedo. We were working more recently on a NATS installer for Kubernetes. So while I was at the booth, I definitely got questions on how can you get started with NATS? You can run the static binary, but we also obviously run on Kubernetes. And I also got some questions on whether we're using stateful sets or daemon sets, stuff like that. If you check out this repo, GitHub nats.io KAS, you can check out exactly what the YAMLs are doing. But if you just kind of trust that all that stuff will work, we have an installer that just kind of runs all the kubectl commands and all that stuff.
Yeah, so I've heard that, noticed some of you are running in production. How many of you are using the NATS operator right now? Okay. So yeah, we'll start doing some changes to NATS operator to move into consolidating more stateful sets. And this is like, if you're not using the operator already, this is like a simple way to just get it started and get like an out-of-the-box, secure by default cluster. We're using the NATS v2 accounts and account installations and TLS setup. So if you're not comfortable just piping into your shell account, into your shell, let's peek at the script, and you'll see that the only requirement is actually a kubectl. We will be kubectl applying the required policy to bootstrap a NAT setup container. That if you have enough policy to be able to run this NAT setup, then you will have just basically create secrets, configuration maps, and among other creating pods and deployments. And so this meta container is going to generate and create the cluster for you, generate the credentials using the NSC common tooling for NATS. So let's start it.
So then we're just running all those kubectl commands, piping into shell, after we carefully inspected that we're not doing anything crazy.
Mm-hmm.
And so on the right-hand side, you can see all the pods and all that stuff coming up on Kubernetes. And on the left-hand side, you can see the commands running.
So yeah, it will create, similar to the NATS operator, I mean, we're just using a headless service for the whole NATS cluster. And we are also deploying a Surveyor, and also has a built-in Grafana dashboard. And all of this is using the secure built-ins, the latest secure built-ins from NATS. It gives you, as a result, a quick walkthrough of how to get started with your cluster. So now I have seen that we have okay, the whole cluster is ready. We have open source, a couple of repos this week. One of them is nats-io KAs repository, and also a NATS box, which is kind of like a busy box analog, some small, very lightweight container with some of the common utilities that you use for NATS. Has utils for publish, subscribe, both to NATS and NATS streaming, and also the NSC, which is the tool you use for managing accounts and users. So the installer will create for you this NATS box that has all the certificates and the generated credentials that you can use to connect to this cluster. And that's on the right-hand side of the screen. Let's first try to send some messages.
So this is, again, NATS box running inside Kubernetes, and it already has all these pre-installed tools that you would use to interact with the NATS system. Yeah, and this is that, it may look as like magic, just trying to doing the publish subscribe here, but it's actually completely secure. So if I try to just netcat into the NATS server and on the 482.22, I get the initial info line from the NATS protocol, but I will get disconnected right away because both the authentication is required, and also I need to do the TLS upgrade for the protocol to work. And actually, you can also see, like Colin mentioned, the text-based protocol here. So it's just like info, and then you have your payload. So in this case, it's encoded in JSON, but this can be whatever you want. And also, the clients just parse text. Yeah. So the installer is generating via some environment variables, some helpers to just do pops up with some good defaults for the cluster. And it has the mounted volumes, the credentials that were generated by the installer. So you can start expecting some of these credentials. For example, you can look at this user is only allowed to publish on the test subject and test a full wildcard subject. So if I try to do the same and publish on another subject, I will get actually a permission violation error. For example, hello. Yeah, I don't have enough permissions. And also within the same box, you have the system account user, which is like this special user and special account that you can use to be able to inspect all of the messages that are flowing through to the system. So it's like a very useful for operations to be able to just collect some metrics that the latest state from the cluster. And it's actually what Surveyor is using to gather all the metrics, all the data using a single Prometheus exporter, rather than having this n number of exporters for per NATS server. And it has the built-in credentials for STAN as well, NATS streaming. So you can publish some var. Well, yeah. A few messages. Hello world again. Then I can replay all of the messages that have been published so far. Yeah, I published some before, so the mounted volumes were already there, and I just replayed the whole thing. Yeah, and just a reminder, the STAN was like NATS, but with persistence, so you could get the replay. And also, can also start using some of the latest features that got merged into the NATS server, as the latency tracking. So I can start a server, a simple service that is only going to be replying with I can help whenever you send a response, whenever you make a request. And again, in NATS, we call a service as a type of subscription that
from which you can await a response or a reply. So in this case, I'm creating a simple service on the test subject, sending a request for help, and I will receive the message. And there's also this special subject that this particular user is able to subscribe to be able to gather metrics about the latency from this subject. So if I subscribe to it, I'll start receiving some of the requests metrics. So I can see that from the 2 forked process that I have, I'm receiving the response. And also I'm receiving on the latency stream that it took a few milliseconds to get the response end-to-end for this single subscription. So I'm going to keep it sending request.
Yeah, so like Colin mentioned also in his presentation, it's NATS is a pub subsystem, but it also does support different patterns. So like an HTTP REST server or something like that, we can also do request-reply type patterns.
And by using the port forwarding, one of your local ports, you can open the Grafana dashboard with some of the default dashboard that are part of the image.
So the NATS installer not only installed NATS, it also did TLS and also installed Surveyor and provided the Grafana dashboards all with that one-liner. Yeah.
And there's an extra dashboard for the latency tracking. So you can modify a Surveyor to tell it to which, what are the subjects that is going to be, for which subjects it is going to be tracking the latency. So it's like really a fast way to just gather some insight on the response time from your services. And so this is a very simple way to just get started. It takes less than 1 minute, I think. For just start using the latest security features from NATS. Yep.
And all of that is open source. All of NATS is open source, so you guys can inspect the code, check out the YAMLs, and all that stuff.
Yeah. So we can move to any questions, or should we?
Yeah, that's it. Thank you.
Yeah. JetStream is our next-gen persistence layer. It's come out of a lot of the experiences that the team has had, both prior to NATS, 20-some years ago, Stan, and then really from you, the community, that's kind of been telling us what you like and what you didn't like. And so JetStream has been in deep code, implementation stage now for, I think, about 2.5, 3 months or so. We've been designing it for about 8. But again, we already had a good set of understanding of what we wanted to do. Colin did a great job of explaining some of the targets that we did. So I want to show you kind of where we are, what you can expect, and then I can actually answer any questions that you might have. So NATS 2.0, as many of you know, is account aware, right? It understands multiple accounts and users and sharing and all that other stuff, and it has a security mechanism around that. However, a lot of people still use NATS in a pre-2.0 type of thing, where it's like, it's for me, I just want to run one server and be able to do things. And so the trick we had with NATS 2.0 is to make NATS 2.0 look like a 1.0, meaning any client, even from 9 years ago, can still run. We wanted to keep that with JetStream, even though JetStream is totally NATS 2.0 aware, bound to accounts, all that kind of fun stuff. And so this is a normal NATS server, and so if you're just wanting to play around with JetStream, this is on a branch right now, it's all open source. You just put -JS in, and the system will automatically figure out kind of what it wants to use potentially from a resource standpoint, mostly around memory. So this is a 16 gig little MacBook, so it says I can use up to 12 gig of the memory, and then there's the store directory. From a concept standpoint, Colin talked about message sets, right, which are how we actually define interest, global order, and retention policies on a group of messages. And then there's observables, how you can actually pull those messages out. And what's interesting about observables, I think, from lessons learned is that we have both push-based, Stan and NATS are all push-based, but we also have pull-based. meaning that you can actually create a message set and say, I want to create an observable that's just going to send a request and get the next message, or get the next 10 messages, or next 100 messages or so. But we start with message sets themselves. So this is a little utility. It's on my laptop. All it's doing is sending normal NATS messages on, pardon me, on a subject space that's been imported automatically into my account. So I might want to add a message set. I'll call it cube. Foo, I always use foo. However, you can have as many as you want. You can have wildcards. Doesn't matter. Whatever you want, you can have. The limit that Collins were talking about, very similar to Stan. So I can say unlimited here, but 1 minute. And then storage is memory or file. We do support memory as a first class system, not just a testing framework, so that when clustering actually hits, if you want, you can have every replica in memory only for very, very high-speed types of situations. But file with SSDs and stuff isn't pokey, so we'll see that. So now if I say JSM info, this is telling me what my account, and by the way, it's all account aware, so I'm just under the covers of bound to the global account, and that's 2.0. That's saying what my account can use, and I'm bound to a single server right here. However, think about something like a supercluster that Colin was talking about. Your account can have so many resources, and they'll be spread across the whole pool of resources from the supercluster itself. I can say list and say which ones are in there, and I see there's cube. I can say info on cube. And you can say there's nothing really there. And so then if we want to go and send some messages, but we need to be able to see this. That's a little bit better. So this is going to go ahead and send 1 million messages of about a K each. And we're sending it to one of the subjects that the message set has been defined around. So that server, remember there's no other servers here, it's just the NAT server, is going to detect that and actually store these things. And so when I go ahead and start at the benchmark, this is a normal NATS bench, by the way. So it's an existing program using all low-level NAT stuff, no special stand stuff or whatever. So it's a little MacBook on battery power, but about 250,000 1K messages a second. We can say info on cube, and you can see that the messages are there. I will kill this, and then if I do this, obviously it's like there's nobody home. I restart it, it's already restored. So it's fast. I can do things like JSM purge. Instantaneously was purged down to 0 messages. So what I'll do is I'll say JSM list. I'll delete cube. And I'll add another one, and I'll call it Derek, and it'll just be on foo. It's only allowed 10 messages. It'll store to disk. So now I have something that sits there and has 5 messages. And this is one of the things that Colin said the community was really talking a lot about. And so I can say nats pub. This is the same thing that comes in the nats box that Wally and Jaime were showing. To foo, hello. And it says published it. And I can say, okay, did I get it in my message set? Yes, I actually got that. Now I can say nats request. And the reason is, and a lot of people who have been in our ecosystem for a while will hear us talk about anti-patterns of if you're doing a request reply, there's really no reason from an interaction standpoint of the request reply to ever store a message, right? You're waiting for an answer. And I say to people that ask me, I say, when you're actually sending a persisted message in a system, you're just doing a request reply to a different entity. That's all. So if we do a nats request to foo, right, there's no listeners on foo or anything, but the system's listening and JetStream's listening, and so it immediately responds with an OK. And now you know the message has been persisted, replicated, and all that other fun stuff. And so again, now on Derek, I've got 2 messages now, so let's send a bunch of them. So we've got 9 messages now, starting at sequence 1, ending at sequence number 9. One of the interesting things about observables, which I won't show a lot, they're all coded and stuff, they're just not in this tool yet. You can tell, like, came under the weather a little bit, so I slowed down, unfortunately, is the fact that observables, like we said, can do push or pull based. They can replay at the original rate that the system receives the messages or instantly. You can do a lot of very interesting things. You can partition the data set if it has lots of subjects. Colin then said, oh, but hey, what about, things like GDPR and what's the ecosystem caring about certain things? Sorry, my original point on observability, was message sets have sequences, right? You can see sequence number 1 through sequence number 9. Observables have their own sequencing, and observables always start at sequence 1, and they always monotonically go up. So you always get 1, 2, 3, 4, 5, or whatever. What's interesting about that and that guarantee that we make is that act mode that Colin pointed out where it said act none and everyone kind of tilted their head a little bit. Act none actually works really well because the system will tell you anytime you've ever lost a message, even if you're partitioning a message set or you're doing a totally different class of observable, because those sequence numbers for your observable are 1, 2, 3, 4, 5, 6. So if you get 8, you know you missed a message and you can immediately request it to come back. In that reply subject, again, this is all core NAT, so there's no protocol buffers, any type of enveloping, encapsulation type thing. The reply subject that you get as an observable when I hand you the message gives you total control of the JetStream system for that message. If you actually look at it, you can see it has delivery count, the store sequence, and your observability sequence. And you're allowed to do things like ACK, NAC, or one of the big things that we put in was the ability to say, hold the phone, I'm working on it. Don't bother me yet. And so if you actually have a mode where you're saying, no, we really want this notion of a minute timeout. If someone's not processed it by then, please re-deliver to someone else, like say in a work queue scenario. This is really interesting because I can know that I only have a minute and I can say, I'm almost done and just send to that reply subject with a progress indicator saying I'm working on it, and it'll reset the timer internally. So it won't actually re-deliver it unless you're actually really, really gone. So back to the message set. So I'm going to delete a message from Derek. Oh, wait a minute. Let me do this because they might all be gone. Nope, they're still there. Okay. So I'll delete number 2, store sequence number 2. What's interesting about this and what's, I think, important in a can we trust this type of system is when we did the 250,000 messages a second, what I didn't say is that they actually are all processed through a hashing mechanism around their timestamp, sequence number, order, everything. So the whole persistent store that JetStream is doing is tamper-proof. You can't mess with it. It knows if you've tampered with anything. And it's on by default. Stan had the ability to turn CRCs off and stuff. This is actually using a highway hash, which can do about 10 gigabytes a second or so per core. And so what I'm doing here is I'm going to say delete this message. And Colin alluded to it, but what this is going to do is it's going to securely pull it out, redo the timestamp, put the sequence number to 0, which is invalid in JetStream, and it'll put random data over top of the message, and it'll restamp it in so it's totally tamper-proof, meaning you can't accidentally put something in there. And so when we do this, we got an okay response, and when we look at the thing now, we only have 8 messages, and 2 is gone. So if I was doing the observability thing, you would see 1, and you as the observer would see 1, 2, 3, 4, but sequence number you'd see 1, 3, 4, 5, 6, 7, or whatever. So we think this is going to be really popular with places that need things like GDPR. The purge command, which I think I showed earlier, is good for someone just did something and ran away and filled up all of our resources in one of these. You don't have to totally blow the channel, or we call these message sets away. You can simply purge it and move on. So hopefully that gives you a little bit of sense of it is real, it exists. We're trying to get this out and merge it in probably in the next couple of weeks for people to start pounding on. The clustering algorithms have been designed. They look great on paper, but that's always the case. But we're going to start coding those up, meaning that we're going to have the clustered stuff in an RC probably very early in Q1, hopefully January, February timeframe. So thank you. Happy to answer any questions you have for me or anyone in the team. I think they did a great job, so thank you guys. I appreciate it. So any questions? Anything at all? Yes?
I I keep hearing geo-aware.
Yep.
Yeah, I keep testing. I keep hearing geo-aware, but I imagine you're just using latency as a proxy for geography. Is that true, or?
So the question is, he keeps hearing about geo-aware, and are we just using latency as a proxy for geo? So there's a couple, sorry, there's a couple pieces involved in this. When you actually connect as a client, that's what we call your source cluster. You're actually sourcing from there. And so in the case of I'm sending a request, the system is aware that the request is coming into this as a source cluster. And so what Colin was talking about is that we'll prefer queue subscribers in that cluster before we fall over to any other clusters. When we do the failover and we go, which one are we going to pick? We do look at the lowest RTT between our source cluster and the destination cluster. Now the second piece of this that you got to combine both pieces to get something that we think is fairly attractive is with NGS, which is again, it's a global supercluster that we run. It's accessible by one URL. So what we do is we run through NS1. When you hit that one URL, we actually figure out where you are on your geo. We figure out if you have a preference for a cloud provider, meaning if you're coming from Google or Amazon, and we return you a CNAME of the local cluster that matches that. So if you combine both of those things, you're actually getting the fastest path into a global supercluster. And then if you send the request, we're doing the right things geographically there, if that makes sense. That's a good question, though. Yes?
You mentioned that it's easy to like do a rolling upgrade or break a cluster down and add a new one up to some of the like server. Like, can you go more into that? Like,
Sure.
Like, because I think it has a replication strategy to put it on top of the replication protocol.
Sure. So the question was upgrading and rolling upgrades of servers. And I think there's a indication.
Like, you're trying to scale up, for example, or like one goes down and like another one comes back up.
Sure. So he was saying one goes down, one comes back up. So in general, Colin spoke to this. The servers gossip amongst themselves, and they share that gossip and that state with clients automatically. So let's say I'm a client and I have his IP and I connect to him. Jaime comes up as another server. He points to Colin. They form their own little mini cluster. I'm immediately aware of Jaime, meaning if Colin goes away, I can fail over there. So most of the time when you're scaling up, you just add the server and it actually takes care of itself. No DNS, no any of that. The clients are all aware. Now going down is probably more interesting. So our servers understand the notion of lame duck mode. Lame duck mode means that came from a saying inside of Google when I was there. It won't accept any new connections, and it eventually starts pruning off the connections it has. So the first thing it's doing to the clients is it says, I'm not accepting any more, and so it updates the client, Jaime, saying, hey, if I go away, don't try me again, I'm not here. But there's Collins here, right? And it'll slowly start pruning these connections. Now, in the future, probably in sometime in 2020, we're going to attempt to make some of the clients extremely intelligent, and the server can give them a hint that they're about to get cut off, and they can proactively reconnect without dropping any data, even though you're doing a once most pattern. The last piece of it, and then I can answer any more after this or offline, is the way we do our superclusters is we actually bring up all three of the new version. We form a 6-node cluster, the full mesh one hop, and then we instantaneously lame duck all of the old ones, meaning all of the clients only move once. They move over to all the new clusters. Then we actually drop all of the old servers, and the new configuration is just the 3-node cluster. So that's how we do that in production. Any others? There's got to be some good ones, some doozies. Yes?
I had a question with scalability. So say that you have a couple of different subscribers, both listening to the same event. Say like a user created, and you have one that you want to index that user perhaps, and then another that's like welcome. Say that you want to do the indexing in near real time. Is it possible to scale up that subscriber and still ensure at least one delivery to both?
So the question was scalability, and you've kind of got two subscribers kind of doing two logistical different types of operations. Can you scale one and still have the properties that you want? So the properties of at least once or at most once is Stan, JetStream, or just NAT's core. That's irregardless. when you talk about multiple participants listening to the same message, a couple things come into play. You can run those independently. So this could be a queue subscriber. You can put 100. And by the way, queue subscribers now, the clients, they've had this for a while, have a really interesting property. Again, when you scale down, is instead of just saying close or quitting, you say drain, which means all of the in-flight messages you'll process and then you'll exit after you're done with that. So even within most processing, you won't, the probability you lose a message is almost zero. It's pretty slick. So those are independent. The other thing that's somewhat common knowledge, but just so we're all on the same page, is that anytime a message comes into a NAT system, this is a cluster, supercluster, doesn't matter, the system is extremely aware and efficient at where the interest lies throughout. So if you have those indexers, let's say, over across a route connection or a gateway connection, that message is only going to go over once, even if you have 1,000 subscribers down the chain, right? So we try to be extremely efficient at only sending messages once when there's interest. And the other thing we do that most people don't do is distributed systems are hard to stretch. And it sounds funny because you're like, it's a distributed system, but most distributed systems, if you try to stretch them where there's variable RTTs in between components, not fixed, bandwidth, sketchy type stuff, usually they don't do well. So our gateway connections are explicitly designed for stretching a NAT system into a supercluster. And what they care deeply about is not only sending the message once, but pruning off interest graph chatter. So what I mean by that is, let's say we're over here and we're doing our thing, we've got publisher subscribers, you're all the way in Asia, you don't care about us, and we're never going to connect over in Asia. So us sending all the chatter about he's interested in foo, no, he's interested in foo, no, bar, no, we prune all of that. And so we actually have a bidirectional spline topology, half duplex, 2 different connections, and we have 2 personalities of the connection that we can change based on trying to make sure we use that bandwidth as efficiently as possible. From a scale perspective, several people asked this of me at the booth. The first thing I look for is bandwidth. Our number one, today this thing was a different number one saying, but the number one saying we usually get is, I thought it would be faster. And I always go, well, what are you trying to do? And I said, well, how big is your NIC? And they're like, it's a 10 gig NIC. And I'm like, yep, and we're sending 8.9 gigabits, which is pretty much the theoretical maximum or so, right? So currently, the way we've tested it, we think we can get to about 60 gigabit. So I think we can flood a 40 gigabit. I don't think we can flood 100 gigabit with a single connection, but we are going to do testing with that. Amazon now has those 100 gigabits, and I think Google has some as well. So first look at your bandwidth, then look at your CPUs. A lot of people like to throw lots of cores at NATs, which is good. The problem is NATs is very efficient, but most machines, when you throw lots of cores, if you light them all up, the thermal thing kicks in and the CPU clock rate drops. So a lot of times you can actually run a benchmark on NATs with like go max prox equals 4, and it'll run faster. And then the last piece is if you've got tens of thousands, hundreds of thousands, you want to do a million connections, it's just memory. You just got to scale the memory. Oh, hold on 1 second, I'll come back to you. Yes?
How does this play with something like Istio? How does something if you're doing request response using the account feature? It's kind of like a service mesh. Is there any use case where we're having Istio and NATs together?
So the question was Istio and NATs, and it's a great question. So if we look fundamentally at HTTP is one-to-one, right? NATs is M-to-N. And we believe deeply in that pattern. We believe how it surfaces looks very familiar to one-to-one, or one-to-N where you're doing load balancing, or M-to-N when you're doing streaming. But fundamentally, it is M-to-N, and we are very specific about that. So in general, we suggest people don't put anything in between the client and our server. You can sometimes, and I'll explain where you can't, or you can't today. Most of the time, the things that Wally is running in Kubernetes, he'll yell at me if I get it wrong, but we use node port, right? Affinity? Host port, sorry. Meaning that you, as a person inside of the Kubernetes cluster, or if you expose it outside, are connecting directly to the server. We don't need any load balancer in front of us. We actually don't want it. We don't want any ingesters and stuff. Now, with Istio, people said, hey, we want to use some of the policies and stuff in Istio. And that's not a bad thing per se. What happens is that if you're a layer 7 router trying to pretend to be a layer 4 router, but you're really not a layer 4 router, bad things happen. And so with Istio, what happens is if you notice when Wally did the low-level telnet and we got the info block back in plain text, that was a design decision I made 10 years ago, and I liked it, meaning even if it was supposed to be TLS or SSL back then, you could get a sense of what was expected of you. Most people will come and kind of kick me in the shins and say, what do you mean? So you auto-upgrade a connection in flight and blah, 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 and yes, we do. And that's what breaks Istio. So if you stick Istio in front of us and you try to make it a TLS, it won't work. Because Istio is going, hey, this doesn't look right, and I have to be able to terminate and resource, and what the heck is this thing doing? So when the people kick me in the shin, I go, well, that's the way SSL works. It's just a fixed plain text header that it sends first. And people can then bake that in and say, ooh, I recognize that as TLS. But ours confuses a lot of TLS proxies that live at layer 7. We're trying to figure out a way to work better with more cloud-native stuff. We have Prometheus and Grafana and FluentD and stuff, but we were looking at OPA, Istio. We've got a lot of those questions. So we're going to try to figure out what makes the most sense and work through that. But when it doesn't work right now, that's why, is because it's saying it can do kind of layer 4 things, but it can't. It's a layer 7. And so when it sees that plain text, it gets confused. So what normally happens downstream is you'll see those info block, and then it'll chop you off. And you're like, what the heck happened? So, no.
And if you look at our feature sets and what we're adding, there is a lot of overlap with service mesh. So a lot of things just by installing NATS you get for free. So you don't necessarily need those bolt-ons.
Yeah, so for example, we've had authorization primitives, permissioning, allow, deny clauses, dynamic response permissioning. You can only publish a response to something that you received. Service mesh then cares about observability. We didn't do a good enough job, and so we really looked at ourselves and said, hey, we need to figure this out. And what we found is that same bias we talked about earlier of distributed systems having this bias where they're actually very close together and there's a fairly consistent RTT and a bandwidth constraint. We run global systems. All of our last 4 or 5 POCs have been multi-region, multi-cloud, global type stuff. And I said, wow, if you just give me the latency of, let's say, Colin the responder, that doesn't help me at all. And so what Wally was showing you is when you export a service, let's say I'm exporting the Colin service, and I go, I want to track latency on that. You can sample at any rate you want. What we're actually providing you is 4 pieces of data. We're providing you with what time it took him to actually service the request. We're going to give you the NATS subsystem, which I'll talk about in a second, and we're going to give you how far away the requester is from the NAT system, how far away he is from the NAT system, and how far the 2 servers, which might not be the same in a large deployment, are from each other. We give you all of that. And RI is here. He was playing with it quite a bit, and he was kind of like looking at me funny, like I don't get it. And then all of a sudden it kind of popped. It's like, oh, if all of a sudden I run a requester in Asia, and you go, Colin, how you doing? Colin's going, I'm doing great. But all of a sudden the total latency went up, but it was because a requester was making requests from way far away. And what that would signal to us is, ooh, we might want to take a Colin and just spin him up in Asia because he's already a Q subscriber, so we don't have to do anything special. If he just starts running over there, the system does the right thing. The last piece of SMI that we do not do yet, but I have a way that we're going to implement soon, is traffic shaping. I want 10% to go to him, 90% to go to me. And that Q group, if you noticed in the presentation I gave, I was giving it a version, like version 0.10 or whatever like that. I think what's going to happen is that you'll be able to decorate the exported service and say, hey, I want you to bind together 2 Q groups, V001 and V002, and give 1% to V002, and then you can change that. So look for that to come up. Okay. Yeah, so we don't have that yet. We don't have traffic shaping yet, but we are on it. We care deeply about the permissioning, but we've always had that. The observability, I mistakenly said, it's a pub subsystem, of course it's easy, and it wasn't. There's a lot of things going on, and inside of the code, if you look at the servers, especially if they're 2 different servers, the requesters over here, responders over here, we have to track 2 latency points and mesh those together in any order in real time and then send the result out. So it was kind of a fun challenge. Yes?
Yeah. So if I understand this correctly, each message gets an incrementing integer inside of a topic or a subject, whatever you call it. How do you do that when there might be multiple publishers, multiple servers on that same topic? It seems like you're not using Raft or something like that.
So the question was, I think about sequencing, and I think you're talking about JetStream or Stan. So the answer is that in core NATs, this has been true since day one, ordering is guaranteed by publisher on a given connection. So if Colin's a publisher and he has a connection into the system and he publishes 1, 2, 3, and I publish A, B, C, those orders are guaranteed anywhere within the system. However, if you're subscribing to foo and bar, you might get totally different interleave versus Wally, right? But our orders are maintained. So the question is, how do you maintain a global order and how do you scale that? So there will be in JetStream clustering a leader election. And let's say we're going to say for message set Derek, Colin is the leader. His job, though, is actually only to do the ordering. So what I mean by that is, let's say we're all servers in this cluster. We're all getting messages. We can independently operate on the information that's shared with us that says we need 3 replicas. So I can get a message and I can actually solicit help to get those 3 replicas. You can solicit, and so we're all doing this at the same time. And when we feel, hey, that message was stored, and we use a highway hash and a timestamp to kind of understand a priority, we all know what that message is. I can then say, ooh, it's replicated 3 times, and all I do is send him a small metadata message saying, consider this one for next in line, and then he stamps the sequence number. Once that happens, a message goes out that then triggers all the observables who are waiting for the next message to say, I can send 10 now, or 11. So we're trying to, yes, the global ordering from a message set perspective does need a leader, right? There's algorithms where we could do different things where we say we don't have to have a leader or consensus. The problem is that in NATs, things are so fast that we would constantly be in conflict resolution in some of those algorithms, meaning it would be slower than Christmas. But we're only going to allow him to say, oh, okay, this hash is next up. Okay, sequence number 9, sequence number 10, sequence number 11. Yes?
Could the NATS account server be extended to integrate with a pre-existing identity server, like an OIDC provider that's already able to provision jobs for its clients?
So the question is, can the account server potentially tie into an existing system? And we've been thinking through that quite a bit. And so just a teeny bit of background information. In operator mode, the NAT servers start up with very little configuration. It's who they trust and how do they resolve an account that they've never seen before. Meaning that if Colin sends me or tries to connect to me and he's part of the Synadia account and I've never seen it, how do I resolve that? And by default, there's 2 major ways right now. One is internally there's a resolver, which is either memory-based or HTTP endpoint, and that could be a CDN, that could be anything you want. Or I get information gossiped to me from other servers. So in other words, in our system, when you update an account, the person who's responsible for updating the account actually sends it out into the cluster, and everyone instantaneously gets the update. Now, to your exact question of what about different JWTs and stuff, we've got a couple folks asking about that. JWTs in our world are public claims, and we fix the signing key to make them secure. Most people will tell you JWTs are fine unless you allow someone to pick the algorithm. That being said, we are trying to look at ways that we might be able to do something a little different to tie into those. Right now, there is no way, but we are looking at it pretty hard and trying to make sure that it fits in with what people want.
And because the account the resolver is based on an HTTP endpoint, we've had, I think, one user write their own account resolver.
And
so that could pull from any source.
Yeah, and those, our JWTs in our system are considered public. So you can put them anywhere you want, and there's, it's just a public claim that unless you actually go through the root of trust, or you try to update it where you need the private key, it's feel free to put it anywhere type stuff.
Just follow up, will any of you be at the Meet the Maintainers so I can talk about contributing something like that?
I think, are you going to be there? Yeah, I think we'll have people there, for sure. And definitely hit us up on Slack. That's usually where we kind of hang out. No, but there's a NAT Slack, so it's a slack.nats.io, and it'll give you a little joining thing and stuff. Yes?
So earlier in the talk, you suggested only once semantics weren't useful or had a lot of performance consequences and weren't necessarily a pattern you wanted to use to implement things.
Or exactly once?
Yes, sorry.
Yep.
So if you want to build a microservice that you're calling with NATS and you want to only perform a side effect one time, what kind of pattern would you suggest to implement that?
You need to be idempotent. And the reason why is even with exactly once, let's say you get halfway through processing the message and you crash. Then you may have a table out of whack. You may have something going on. Let's say you get all the way through processing the message and you crash before you act. You're going to get that message back. Or let's say that message has come in and it's in the process of being sent to you processing and you crash. You don't know what happened there. So you still have to be idempotent. So then why do you need exactly once?
Yeah, so in a prior life at TIBCO, I created EMS which had exactly once and also had XA, meaning you could coordinate multiple resources. We deployed it. I think at the time it cost $32 million for this customer. And I told him, I said, I built it for you, but I said, you're not going to use it. And they said, that's what we wanted. And he puts it in. Calls less than 2 weeks later, says, come back. I had to fly back to the middle of the country, spend 6 weeks there. And what we did was we designed a compensating transaction model. So in other words, you never rolled back, you always just kept rolling forward. And then, some of the things that Colin was talking about can help there. So either idempotent, meaning I can keep saying the same thing and it's your side effect free, or I would suggest maybe even, what's it called, CQR? Yeah, which is hard to model your stuff, or compensating transactions is the most normal way I would probably approach it. Yes?
When you're using access like, for example, service mesh, right? Or one of the topics on the service mesh is MTLS, right? Where it's not necessarily your authentication with the NAS server, but with who can receive my message or my request, right? It's between the two clients of the message. Do we have anything today? Do we have anything on the plan or the roadmap, or any, I would say, alternative to approach that without on the client, between the client?
Sure. So the question is about permissioning and MLTS, and is there something kind of putting those together? When you're on the web and you go to your bank site, you don't have a client cert, right? You authenticate yourself to the bank some other different way, and your browser can trust that it's really the bank. Most of the world exists that way because managing certs and actually being able to embed permissioning inside of certs is a capital PITA, right? So no one really does it. However, it is useful to say, hey, I want to be able to bidirectionally trust that, hey, I'm trying to connect to you and you're trusting me, that I'm allowed to do that. So within NATS today, we do support client-side certs, and we do have the ability to pull identity out of that client-side cert. However, you still have an authorization stanza that needs to live somewhere. So when people come to us, we had a gentleman doing some really cool stuff, and he was doing MLTS, and he's like, oh, now I'm going to add permissioning into the JWT and stuff. And I said, hey, you don't need MTLS. He goes, yes, I do. I said, no, you don't. I said, the client cares about connecting to the server, but the server only cares about the client if it can properly authenticate with E25519 keys, all the other stuff. And that JWT that you send in, we check all the way up to the root of trust, the operator, it has all your claims as I can publish to foo, I can receive on this, that kind of stuff. So if you're looking at a service mesh, which we have a lot of folks doing, where the responders are NATS clients, right, they listen, we definitely suggest TLS, especially for client to server. You can do MTLS, by the way, within clusters if you want, or VPC. A lot of times VPCs are fine. But we usually say if you care deeply about permissioning of, hey, I have a connection, but now I want to make sure I'm allowed to do things inside of that with different subjects, use the authorization primitives that we put together. We've passed about 6 really nasty customer security audits where most people got kicked out pretty quickly, and we were beat up a little bit, but we survived. If MLTS is still what you want, and you say, no, I need these certificates, and the authorization is small, what you can do is set up MLTS and then say, I'm going to pull out the identity from the certificate of who the user is. Let's say Wally. And Wally did some of the work, so grab him if you need more answers. But then you still need to configure the authorization that applies to Wally. And so that's either going to be a config file and all. And so with NATS 2.0 being totally decentralized and distributed, we're like, it should be in this claim JWT that you're sending in as a client app. So we usually suggest that. Yep. Any others? Yes?
Where do you guys need the most help in the open source community?
The question is, where do we need the most help?
Oh,
I was just going to say awareness.
yeah.
So it's amazing. I mean, those who know us, especially know me on Twitter, it's probably, Nats 7x24 and sprinkled in with a couple other things. But if someone else says, hey, I use this, and that stuff just works. It's rock solid. It just works. That amplifies the signal so much. So if you've used it and you liked it, speak up. If you used it and you didn't like it, speak up too, right? Because we can learn more from that. And we try to be extremely helpful on the Slack channels and responsive, but at least from my perspective, awareness.
This falls in the awareness bucket, but sharing your use case, sharing how you started, what worked, what didn't, what performed, what didn't, that provides that's highly valuable to the rest of the community. So those are things we're looking for too.
Yeah. Well, there's an amazing amount of people that use it in production. They run a single server, don't even monitor it, and it runs for 2 years. And they shut the whole system down, and they say, oh, should we upgrade it? And they just run it again for 2 more years type stuff. So, but yeah, if there's a use case that you think we might be, helpful on, try it, kick the tires. If you want feedback, we try to be extremely responsive in the Slack channels. We'd like to see you use it. We think it's, extremely helpful. We've had about 5 or 6 customers who we've saved about 80 to 90% of their cloud bill. All right, so that 80 million messages a second, nobody really cares about that until you have to, it translates to how much you pay. How big of a machine do I need? This thing will run, if you want to do 50,000, 100,000 messages a second, you can do that on a Raspberry Pi. You can do it on a T2 Nano, I think. Mm-hmm. And we have benchmarks that you can just run it yourself and test it. And so we got a lot of people saying, we just want to concentrate on stuff that makes us unique and our business better and our value prop, and not have to worry about a lot of that stuff. We fit really well into that. Yes?
Are there specific semantics about setting up clusters versus superclusters, or is that determined automatically? Like the topology of those?
So the question is clusters and superclusters, and I'll point you at Wally, who's probably done the most setup of those. You can configure such that everybody knows about everyone else, and their configure files are pretty lengthy. For our supercluster, the gateways are the same for every single server, because if we detect ourselves, we drop the connection or don't even attempt it. So, and I think we do full mesh, meaning the config for a small cluster knows about all of them. However, what we do also is we provide seed nodes. So what I mean by that is take a DNS record, start 1, maybe 2, 3, or whatever, and put those in the DNS. And then every new server that you want to join the cluster, just point it at that DNS. It'll get hold of one of you 3, and you'll gossip to all the other one, and it'll immediately put itself together. It's really slick how that works. Gateways kind of do the same thing. If you just get over there, it'll all put itself together. So you have choices there.
And generally, clusters within a region where you've got a lot of bandwidth you can use, gateways are cross WANs. I mean, that's the general rule of thumb.
Yeah, but leaf nodes are a extend and embrace type of a thing, which again, they're really slick. They totally transparently bind into a supercluster, handle all the credentials and all that stuff. So what I do is I amortize TLS for all the tools that I run. On my laptop, I have a leaf node server. So that leaf node server knows my credentials, connects into the supercluster, and then that server runs on 127.0.0.1, no auth. I have to have physical access to my machine, but I can run all the tools for NGS on my thing with nothing, and they're instant, because the amortization of the TLS is already there. It's just been stuck up. Otherwise, TLS, back and forth, credentials, the nonce and stuff, and it was feeling a little sluggish. So we did that. However, Colin brought up the even better point of extending those into like an edge to IoT. And that doesn't have to mean, like little plant sensors. It could be just software you deploy to the field, or a hardware-software combination you deploy to the field. Any others? Thank you guys so much. I really appreciate it.
Thank you for your time.